Work and power notes. So the first thing that we're going to do is we're going to work we covered last time. So what we're going to do is just write a definition of work because we're looking at how work and power are related. So work is a transfer of energy by mechanical means. Okay, so you are basically taking energy and you're using it to create some kind of change in your environment. You're using it to do something, all right? So as far as your calculation, it was the product of force and distance that are parallel to each other. So I'm just going to put that it's force times distance. Parallel to each other. Work equals force times distance. A transfer of energy by mechanical means. It is force times distance, but the force and the distance moved have to be parallel to each other. And keep in mind that work is a scalar quantity. Scalar quantity has magnitude, no direction. All right, the question is, how does the work compare for these? So yes, you have to write this down. How does the work compare for these? Moving an entire stack of books from floor to shelf. Let's say I have a stack of 10 books. So if I move the entire stack all together from the floor to a shelf, or if I'm still talking about the same 10 books, if I move the books one at a time from floor to shelf. So how do you think the work is going to compare? I'm going to give you a minute to go ahead and copy this down, and then we'll talk about it. Okay, so what do you think? How is the work going to compare? Do you think A is going to require more work, B is going to require more work, or do you think they will be the same? The work will be the same. Raise your hand if you think that, as far as A, moving the entire stack of books is going to require more work. Okay. What about moving them one at a time? Same number of books, but you're moving them individually. Who thinks that'll take more work? All right. And then how many think that it will be the same for both? Okay. So what is the equation for work? It's force times distance. Okay, so as far as the force, how would you calculate the force for this? It's the weight, right? Which is going to be mass times gravity. So we have the weight, mass times gravity, for the whole stack, times your distance or your displacement, all right? So both of these, displacement is going to be the same, right? Okay, so what if I take each book individually? So it's the weight of each book individually, moving the same distance, but then I add them all up. It's going to be the same. All you're doing is it's going to take more time because you're doing them individually, but weighing the books, doing the books individually, right, may decrease the initial, the weight, but what happens is you're still moving the entire stack. So eventually the force is going to be the same. Does everyone understand that? Okay, so basically what you're doing is I'm splitting it up. So I'm working with requiring less force, but now I'm doing it multiple times. All right? But in the end, since it's the same stack of books, your force is total is going to be the same. The displacement is the same. All right? So then therefore the work required to do both of these, whichever way you choose, is still going to be the same. So the work required Okay, so we said the work will be the same. Why? Why is it going to be the same? In and the N-I-N. Or ultimately. Okay, so work equals force times distance, and your force is your weight. And ultimately, the force required and the displacement are the same for both. Okay. Work will be the same because work equals your force times your distance, which is your weight. Force is weight. And ultimately, the force required and the displacement are the same for both. Okay. It's just a matter of, are you going to move the entire stack at the same time, or split them up, do them individually, and then add up all those later on. Okay, if you've got that, you can go ahead and set the next part. The next part is for power. So up here, I'm going to have a definition of what power is, write the equation, and then have the rest of this. All right, so power is the change in energy divided by the time. So change in energy divided by the time that is required for the change. Again, it's the change in energy divided by the time required for that change. The change in energy required, or the change in energy divided by the time required for the change. And the equation looks like this. It's power. P for power is the change in your energy divided by your time. Okay, so I'll write that over here. Power equals change in energy divided by time. All right, so the equation that I gave you earlier says that work is force times your displacement, right? But from the, when you did the kinetic energy notes last time, we're looking at the work energy theorem, okay? How does work and kinetic energy, how do they relate? Work equals what? In terms of kinetic energy, work equals what? It's the change in kinetic energy. So when we say here, as far as power, power is your change in energy, we could be talking about our kinetic energy, right? Change in kinetic energy, which is change in kinetic energy is your work divided by time. So when work causes the change in energy, the equation becomes power equals, again, the change in energy, specifically the kinetic energy, or we'll talk about another form of energy later on. So it's a change in energy. If it's caused by work, then the power becomes power equals work divided by time. Okay, power equals work divided by time. All right, so the units of measurement for work, for power is watts. Okay, so we have, I'll write the equation again. So we have, this is in watts. Power is measured in watts, which is the same as what? Work is measured in what units? Joules over time. What's our standard for time? Time. Seconds. Okay, so a watt. The symbol for watt is a capital W, so be careful, all right? So this could stand for the unit of measurement for power, or it could be for work, W for work, depending on which one you're talking about. Are you talking about the variable, or are you talking about a unit of measurement? So in this case, a watt equals a joule per second. My apologies. All right, so for the book example above, we had just said that the work that is done in both cases is going to be the same, right? Because the force is, even though we're splitting it up into smaller chunks for the second example, overall, ultimately what's happening is you're using the same amount of force, okay? And it's the same displacement, so the work is going to be the same. But now if we look at it from the point of view of your power, which is going to be your work divided by the time. So for the book example above, which develops more power? Which one's going to have a bigger power? When we move all the books together, or when we take them and move them individually? Which is going to have a bigger power measurement? All the books together, because when you do it all at once, it's going to take less time, right? Okay, if you're doing them individually, it's going to take more time, so that means less power. So moving all the books together. Because it requires less time. Okay, your example, your practice is the last thing you need to write down. I'll give you a moment to write that, and then we'll go over it. All right, once again, an electric motor lifts an elevator 9 meters in 15 seconds by exerting an upward force of 1.20 times 10 to the fourth newtons. What power does the motor produce in kilowatts? All right, so the first thing that we need to do is we need to make our list. I'm just going to put the list over here. So we have 9 meters, which is what? That's your distance or your displacement. So delta D equals 9 meters. 15 seconds is, time is 15 seconds. Exerting an upward force of 1.20 times 10 to the fourth newtons. That is your force. And then what are we looking for? we're looking for. You're looking for power. All right. And this needs to be in kilowatts. Now, initially when we're using this, all right, when we're solving for power, what will our units come out to be? Watts. So when you're finished, make sure that you convert it to kilowatts. Okay, so what equation are we using? Power equals what? Your work divided by time? And work is what? Work. That's your force times your displacement, right? Divided by time. Okay, so we have force. Times your distance, 9 meters. Divided by 15 seconds.
Yeah.
All right, go ahead and plug that into your calculator, see what you get. Okay, it comes out to 7,200 joules per second, Newton meter over seconds, joules per second, or watts. 7,200 watts. And how do I go from watts to kilowatts? Divide by 1,000. So this becomes what? 7.2 kilowatts. And don't forget to box your answer. Yes?
You divide that by 1,000, right?
You divide by 1,000. Watts is a lot smaller than kilowatts, so to change it to a bigger unit, you divide. To change it to a smaller unit, you multiply. Okay? So divide by 1,000. All right, any questions?